Surface plasmon polaritons, SPPs, are infrared visible frequency electromagnetic waves, which travel along a metal-dielectric or metal-air interface. The term, surface plasmon polariton, explains that the wave involves both charge motion in the metal surface plasmon, and electromagnetic waves in the air or dielectric polariton. They are a type of surface wave, guided along the interface in much the same way that light can be guided by an optical fiber. SPPs are shorter in wavelength than the incident light photons. Hence, SPPs can have tighter spatial confinement and higher local field intensity. Perpendicular to the interface, they have subwavelength-scale confinement. An SPP will propagate along the interface until its energy is lost either to absorption in the metal or scattering into other directions, such as into free space. Application of SPPs enables subwavelength optics in microscopy and lithography beyond the diffraction limit. It also enables the first steady-state micromechanical measurement of a fundamental property of light itself, the momentum of a photon in a dielectric medium. Other applications are photonic data storage, light generation, and bio-photonics. Excitation. SPPs can be excited by both electrons and photons. Excitation by electrons is created by firing electrons into the bulk of a metal. As the electrons scatter, energy is transferred into the bulk plasma. The component of the scattering vector parallel to the surface results in the formation of a surface plasmon polariton. For a photon to excite an SPP, both must have the same frequency and momentum. However, for a given frequency, a free space photon has less momentum than an SPP because the two have different dispersion relations. See below. This momentum mismatch is the reason that a free space photon from air cannot couple directly to an SPP. For the same reason, an SPP on a smooth metal surface cannot emit energy as a free space photon into the dielectric, if the dielectric is uniform. This incompatibility is analogous to the lack of transmission that occurs during total internal reflection. Nevertheless, coupling of photons into SPPs can be achieved using a coupling medium such as a prism or grating, to match the photon and SPP wave vectors, and thus match their momenta. A prism can be positioned against a thin metal film in the Kretschmann configuration or very close to a metal surface in the Otto configuration. Figure 1. A grating coupler matches the wave vectors by increasing the parallel wave vector component by an amount related to the grating period. Figure 2. This method, while less frequently utilized, is critical to the theoretical understanding of the effective surface roughness. Moreover, simple isolated surface defects such as a groove, a slit or a corrugation on an otherwise planar surface provides a mechanism by which free space, radiation and SPs can exchange energy and hence couple fields in dispersion relation. The properties of an SPP can be derived from Maxwell's equations. We use a coordinate system where the metal dielectric interface is the Z equals 0, display style Z equals 0, plane, with the metal at Z less than 0, display style Z less than 0, and dielectric at Z greater than 0, display style Z greater than 0. The electric and magnetic fields as a function of position x, y, z, display style x, y, z, closing curly bracket, and time tr as follows: E x n x y z t equals E 0 E I k x x plus I k z n pipe z pipe minus I omega t display style E underscore x n x y z t equals e underscore 0 e caret ik underscore x plus ik underscore z n z I omega t e z n x y z t equals plus or minus e 0 k x k z n e I k x x plus I k z n pipe z pipe minus I omega t display style e underscore z n x y z t equals pm e underscore 0 frac k underscore x k underscore z n e caret ik underscore x plus ik underscore z n z I omega t h y n x y z t equals h 0 e I k x x plus I k z n pipe z pipe minus I omega t display style h underscore y n x y z t equals h underscore 0 e caret ik underscore x plus ik underscore z n z I omega t, where n indicates the material, 1 for the metal at z less than 0 display style z less than 0, or 2 for the dielectric at z greater than 0 display style z greater than 0. Omega is the angular frequency of the waves. The plus or minus display style pm is plus for the metal. For the dielectric, e x e z display style e underscore x e underscore z are the x and z components of the electric field vector. H y display style h underscore y is the y component of the magnetic field vector, and the other components e y h x h z display style e underscore y h underscore x h underscore z are 0. In other words, SPPs are always trademark transverse magnetic waves. K is the wave vector. It is a complex vector, and in the case of a lossless SPP, it turns out that the x components are real and the z components are imaginary. The wave oscillates along the x direction and exponentially decays along the z direction. K x display style k underscore x is always the same for both materials, but k z 1 display style k underscore z 1 is generally different from k z 2 display style k underscore z 2 h 0 e 0 equals minus epsilon 1 omega k z 1 c display style frac h underscore 0 e underscore 0 equals frac var epsilon underscore 1 omega k underscore z 1 c, where epsilon 1 display style var epsilon underscore 1 is the permittivity of material 1, the metal, and c is the speed of light in vacuum, as discussed below. This can also be written h 0 e 0 equals epsilon 2 omega k z 2 c display style frac h underscore 0 e underscore 0 equals frac var epsilon underscore 2 omega k underscore z 2 c. A wave of this form satisfies Maxwell's equations only on condition that the following equations also hold: k z 1 epsilon 1 plus k z 2 epsilon 2 equals 0. display style frac k underscore z1 var epsilon underscore 1 plus frac k underscore z2 var epsilon underscore 2 equals 0, and k x 2 plus k z n 2 equals epsilon n omega c 2 n equals 1 2. Display style k underscore x caret 2 plus k underscore zinc caret 2 equals var epsilon underscore n left frac omega c right caret 2 q quad n equals 12. Solving these two equations, the dispersion relation for a wave propagating on the surface is k x equals omega c epsilon 1 epsilon 2 epsilon 1 plus epsilon 2 1 slash 2. Display style k underscore x equals frac omega c left frac var epsilon underscore 1 var epsilon underscore 2 var epsilon underscore 1 plus var epsilon underscore 2 right caret 1/2. Closing curly bracket. In the free electron model of an electron gas, which neglects attenuation, the metallic dielectric function is epsilon omega equals 1 minus omega p 2 omega 2. Display style var epsilon omega equals 1 frac omega underscore p caret 2 omega caret 2. Closing curly bracket, where the bulk plasma frequency in SI units is omega p equals n e 2 epsilon 0 m. Display style omega underscore p equals sqrt frac n caret 2 var epsilon underscore 0 m caret asterisk, where n is the electron density, E is the charge of the electron, m asterisk is the effective mass of the electron, and epsilon 0 display style var epsilon underscore 0 is the permittivity of free space. The dispersion relation is plotted in figure 3. At low k, the SPP behaves like a photon, but as k increases, the dispersion relation bends over and reaches an asymptotic limit called the surface plasma frequency. Since the dispersion curve lies to the right of the light line, omega equals kc, the SPP has a shorter wavelength than free space radiation, such that the out-of-plane component of the SPP wave vector is purely imaginary and exhibits evanescent decay. The surface plasma frequency is the asymptote of this curve, and is given by omega s p equals omega p slash 1 plus epsilon 2. Display style omega underscore sp equals omega underscore p sqrt 1 plus var epsilon underscore 2. Closing curly bracket. In the case of air, this result simplifies to omega s p equals omega p slash 2. Display style omega underscore sp equals omega underscore p sqrt 2. Closing curly bracket. If we assume that epsilon 2 is real and epsilon 2 greater than 0, then it must be true that epsilon 1 less than 0. A condition which is satisfied in metals. Electromagnetic waves passing through a metal experience damping due to ohmic losses and electron core interactions. These effects show up in as an imaginary component of the dielectric function. The dielectric function of a metal is expressed epsilon 1 equals epsilon 1 plus I epsilon 1, where epsilon 1 and epsilon 1 are the real and imaginary parts of the dielectric function, respectively. Generally, epsilon 1 greater than epsilon 1, so the wave number can be expressed in terms of its real and imaginary components as k x equals k x single quote plus I k x quote equals omega c epsilon 1 single quote epsilon 2 epsilon 1 single quote plus epsilon 2 1 slash 2 plus I omega c epsilon 1 single quote epsilon 2 epsilon 1 single quote plus epsilon 2 3 slash 2 epsilon 1 quote 2 epsilon 1 single quote 2 display style k underscore x equals k underscore x plus ik underscore x equals left frac omega c left frac the epsilon underscore 1 var epsilon underscore 2 var epsilon underscore 1 plus var epsilon underscore 2 right caret 1/2 right plus I left frac omega c left frac the epsilon underscore 1 var epsilon underscore 2 var epsilon underscore 1 plus var epsilon underscore 2 right caret 3/2 frac the epsilon underscore 1 2 the epsilon underscore 1 caret 2 right closing curly bracket. The wave vector gives us insight into physically meaningful properties of the electromagnetic wave, such as its spatial extent and coupling requirements for wave vector matching, propagation length and skin depth. As an SPP propagates along the surface, it loses energy to the metal due to absorption. The intensity of the surface plasmon decays with the square of the electric field. So at a distance x, the intensity has decreased by a factor of exp opening curly bracket minus 2 k x x closing curly bracket text style exp 2k underscore x x. The propagation length is defined as the distance for the SPP intensity to decay by a factor of 1 e. This condition is satisfied at a length L equals 1 2 k x quote display style L equals frac 1 2 k underscore x closing curly bracket. Likewise, the electric field falls off evanescently perpendicular to the metal surface. At low frequencies, the SPP penetration depth into the metal is commonly approximated using the skin depth formula. In the dielectric, the field will fall off far more slowly. The decay lengths in the metal and dielectric medium can be expressed as Z I equals lambda 2 pi pipe epsilon 1 single quote pipe plus epsilon 2 epsilon I 2 1 slash 2 display style Z underscore I equals frac lambda 2 pi left frac the epsilon underscore 1 plus var epsilon underscore 2 var epsilon underscore I caret 2 right caret 1/2, where I indicates the medium of propagation. SPPs are very sensitive to slight perturbations within the skin depth, and because of this, SPPs are often used to probe inhomogeneities of a surface. Animations, experimental applications, nanofabricated systems that exploit SPPs demonstrate potential for designing and controlling the propagation of light in matter. In particular, SPPs can be used to channel light efficiently into nanometer-scale volumes, leading to direct modification of resonate frequency dispersion properties, substantially shrinking the wavelength of light and the speed of light pulses, for example, as well as field enhancements suitable for enabling strong interactions with nonlinear materials. The resulting enhanced sensitivity of light to external parameters, for example, An applied electric field of the dielectric constant of an adsorbed molecular layer shows great promise for applications in sensing and switching. Current research is focused on the design, fabrication, and experimental characterization of novel components for measurement and communications based on nanoscale plasmonic effects. These devices include ultra-compact plasmonic interferometers for applications such as biosensing, optical positioning and optical switching, as well as the individual building blocks, plasmon source, waveguide and detector, needed to integrate a high-bandwidth, infrared-frequency plasmonic communications link on a silicon chip. In addition to building functional devices based on SPPs, it appears feasible to exploit the dispersion characteristics of SPPs traveling in confined metal-dielectric spaces to create photonic materials with artificially tailored bulk optical characteristics, otherwise known as metamaterials. The excitation of SPPs is frequently used in an experimental technique known as surface plasmon resonance (SPR). In SPR, the maximum excitation of surface plasmons are detected by monitoring the reflected power from a prism coupler as a function of incident angular wavelength. This technique can be used to observe nanometer changes in thickness, density fluctuations, or molecular absorption. Surface plasmon-based circuits, including both SPPs and localized plasmon resonances, have been proposed as a means of overcoming the size limitations of photonic circuits for use in high-performance data processing nano-devices. The ability to dynamically control the plasmonic properties of materials in these nano-devices is key to their development. A new approach that uses plasmon-plasmon interactions has been demonstrated recently. Here the bulk plasmon resonances induced are suppressed to manipulate the propagation of light. This approach has been shown to have a high potential for nanoscale light manipulation and the development of a fully CMOS-compatible electro-optical plasmonic modulator. CMOS-compatible electro-optic plasmonic modulators will be key components in chip-scale photonic circuits. In surface second harmonic generation, the second harmonic signal is proportional to the square of the electric field. The electric field is stronger at the interface because of the surface plasmon, resulting in a nonlinear optical effect. This larger signal is often exploited to produce a stronger second harmonic signal. The wavelength and intensity of the plasmon-related absorption and emission peaks are affected by molecular adsorption that can be used in molecular sensors. For example, a fully operational prototype device detecting casein in milk has been fabricated. The device is based on monitoring changes in plasmon-related absorption of light by a gold layer. Materials used. Surface plasmon polaritons can only exist at the interface between a positive permittivity material and a negative permittivity material. The positive permittivity material, often called the dielectric material, can be any transparent material such as air or, for visible light, glass. The negative permittivity material, often called the plasmonic material, may be a metal or other material. It is more critical, as it tends to have a large effect on the wavelength, absorption length, and other properties of the SPP. Some plasmonic materials are discussed next. Metals. For visible and near-infrared light, the only plasmonic materials are metals, due to their abundance of free electrons, which leads to a high plasma frequency. Materials have negative real permittivity only below their plasma frequency. Unfortunately, metals suffer from ohmic losses that can degrade the performance of plasmonic devices. The need for lower loss has fueled research aimed at developing new materials for plasmonics and optimizing the deposition conditions of existing materials. Both the loss and polarizability of a material affect its optical performance. The quality factor Q S P P _Q SPP for a SPP is defined as epsilon (2 epsilon) frac var epsilon (2 var epsilon). The table below shows the quality factors and SPP propagation lengths for 4 common plasmonic metals: Al, Ag, O and Cu deposited by thermal evaporation under optimized conditions. The quality factors and SPP propagation lengths were calculated using the optical data from the Al, Ag, O and Cu films. Silver exhibits the lowest losses of current materials in both the visible, near-infrared, near, and telecom wavelengths. Gold and copper perform equally well in the visible and near, with copper having a slight advantage. At telecom wavelengths, gold has the advantage over both silver and copper of being chemically stable in natural environments, making it well suited for plasmonic biosensors. However, an interband transition at approximately 470 nanometers greatly increases the losses in gold at wavelengths below 600 nanometers. Aluminum is the best plasmonic material in the ultraviolet regime, less than 330 nanometers, and is also CMOS compatible along with copper. Other materials. The fewer electrons a material has, the lower, i.e., longer wavelength, its plasma frequency becomes. Therefore, at infrared and longer wavelengths, various other plasmonic materials also exist besides metals. These include transparent conducting oxides, which have typical plasma frequency in the near SWIR infrared range. At longer wavelengths, semiconductors may also be plasmonic. Some materials have negative permittivity at certain infrared wavelengths related to photons rather than plasmons, so-called Restralen bands. The resulting waves have the same optical properties as surface plasmon polaritons, but are called by a different term: surface photon polaritons. Effects of roughness. In order to understand the effect of roughness on SPPs, it is beneficial to first understand how a SPP is coupled by a grating. Figure 2. When a photon is incident on a surface, the wave vector of the photon in the dielectric material is smaller than that of the SPP. In order for the photon to couple into a SPP, the wave vector must increase by delta k equals k s p minus k x photon. Display style delta k equals k underscore s p k underscore x. Text photon. The grating harmonics of a periodic grating provide additional momentum parallel to the supporting interface to match the terms k s p p equals k x photon plus or minus n k grating equals omega c sin theta 0 plus or minus n 2 pi a. Display style k underscore SPP equals k underscore x. Text photon PMN k underscore text grating equals frac omega c sin theta underscore 0 PMN frac 2 pi a, where k grating display style k underscore text grating is the wave vector of the grating. Theta 0 display style theta underscore 0 is the angle of incidence of the incoming photon. A is the grating period, and n is an integer. Rough surfaces can be thought of as the superposition of many gratings of different periodicities. Kretschmann proposed that a statistical correlation function be defined for a rough surface g x y equals 1 a z x single quote y single quote, z, x, single quote, minus, x, y, single quote, minus, y, d, x, single quote, d, y, single quote, display style g, x, y, equals frac 1 a int underscore a z, x, y, z, x, x, y, y, backslash, dx, dy, where, z, x, y, display style z, x, y, closing curly bracket, is the height above the mean surface height at the position x, y, display style x, y, closing curly bracket, and a, display style a, is the area of integration, assuming that the statistical correlation function is Gaussian of the form g, x, y, equals delta 2 exp minus r 2 sigma 2, display style g, x, y, equals delta caret 2 exp left frac r caret 2 sigma caret 2 right, closing curly bracket, where delta, display style delta, is the root mean square height, r, display style r, is the distance from the point x, y, display style x, y, closing curly bracket, and sigma, display style sigma, is the correlation length. Then the Fourier transform of the correlation function is pipe s k surf pipe 2 equals 1 4 pi sigma 2 delta 2 exp minus sigma 2 k surf 2 4 display style s k underscore text surf caret 2 equals frac 1 4 pi sigma caret 2 delta caret 2 exp left frac sigma caret 2 k underscore text surf caret 2 4 right, closing curly bracket, where s, display style s, is a measure of the amount of each spatial frequency k surf, display style k underscore text surf, which help couple photons into a surface plasmon. If the surface only has one Fourier component of roughness, i.e., the surface profile is sinusoidal, then the s, display style s, is discrete and exists only at k equals 2 pi a, display style k equals frac 2 pi a, resulting in a single narrow set of angles for coupling. If the surface contains many Fourier components, then coupling becomes possible at multiple angles. For a random surface, s, display style s, becomes continuous and the range of coupling angles broadens. As stated earlier, SPPs are non-radiative. When a SPP travels along a rough surface, it usually becomes radiative due to scattering. The surface scattering theory of light suggests that the scattered intensity d, I, display style di, per solid angle, d, omega, display style d, omega, per incident intensity, I, 0, display style I underscore 0, is d, I, d, omega, I, 0, equals 4, epsilon, 0, cos, theta, 0, pi, 4, lambda, 4, pipe, t, 012, p, pipe, 2, pipe, w, pipe, 2, pipe, s, k, surf, pipe, 2, display style frac di d omega I underscore 0 equals frac 4 sqrt ver epsilon underscore 0 cos theta underscore 0 frac pi caret 4 lambda caret 4 t underscore 012 caret p caret 2 w caret 2 s k underscore text surf caret 2 where pipe w pipe 2 display style w caret 2 is the radiation pattern from a single dipole at the metal-dielectric interface. If surface plasmons are excited in the Kretschmann geometry and the scattered light is observed in the plane of incidence, Fig. 4, then the dipole function becomes pipe w pipe 2 equals a theta pipe epsilon 1 pipe sin 2 psi 1 plus sin 2 theta slash pipe epsilon 1 pipe 1 slash 2 minus sin theta 2 display style w caret 2 equals a theta the epsilon underscore 1 sin caret 2 psi 1 plus sin caret 2 theta the epsilon underscore 1 caret 1/2 sin theta caret 2 with a theta pipe epsilon 1 pipe equals pipe epsilon 1 pipe plus 1 pipe epsilon 1 pipe minus 1 4 1 plus tan theta slash pipe epsilon 1 pipe display style a theta the epsilon underscore 1 equals frac the epsilon underscore 1 plus 1 the epsilon underscore 1 minus 1 frac 4 1 plus tan theta the epsilon underscore 1 where psi display style psi is the polarization angle and theta display style theta is the angle from the z-axis in the xz plane. Two important consequences come out of these equations. The first is that if psi equals 0 display style psi equals 0 s polarization, then pipe w pipe 2 equals 0 display style w caret 2 equals 0 and the scattered light d omega I 0 equals 0 display style frac d omega I underscore 0 equals 0. Secondly, the scattered light has a measurable profile which is readily correlated to the roughness. This topic is treated in greater detail in reference. See also surface plasmon resonance, localized surface plasmon, plasmonic len, superlens. References. Further reading. Ebsen, T. W. Lezik, H. J. Garami, H. F. Thio, T. Wolf, P. A. 1998. Extraordinary Optical Transmission Through Subwavelength Whole Arrays. PDF. Nature. 391. 6668. 667. Bibcode. 1998 Nature. 391. 667e. DOI. 10.1038 35570. Hendry, E. Garcia Vidal, F. Martin Moreno, L. Rivas, J. Bon, M. Hibbons, A. Lockyer, M. 2008. Optical Control over Surface Plasmon Polariton-Assisted THZ Transmission Through a Slit Aperture. PDF. Physical Review Letters. 100. 12. 123901. Bibcode. 2008 PHRVL. 100 L3901H. DOI. 10.1103. Physrevlet. 100.123901. PMID 18517865. Free PDF download. Barnes, William L. Daru, Alan, Ebsen, Thomas W. 2003. Surface Plasmon Subwavelength Optics. PDF. Nature. 424. 6950. 824-30. Bibcode. 2003 Nature. 424. 824b. DOI. 10.1038 Nature 01937. PMID 12917696. Free PDF download. Pitarch, J.M., Silkin, V.M., Cholkov, E.V., Eshnik, P.M., 2007. Theory of Surface Plasmons and Surface Plasmon Polaritons. PDF. Reports on Progress in Physics. 71. Arxiv. Cond. Mat. 0611257. Bibcode. 2007 RPPH. 71p. DOI. 10.1088-0034-4885-70/1, R01. Free PDF download. External links. White, Justin. March 19, 2007. Surface Plasmon Polaritons. Online. Stanford University. Physics Department. Submitted as coursework for AP 272. Winter 2007.